Hello, class. I wanted to continue on with our lecture in section 1.6, which in this particular case deals with solving rational equations that lead to quadratic equations. All right, I have this off to the side, and you can find this in our OneNote notebook in the case that you're wondering. So let's just kind of take a look at this problem and see what we have going on. So you know the classic way that we solve any type of problem that has fractions, whether they be constants, or in the denominator, the constants in the denominator, or they be algebraic expressions in the denominator. We look to multiply both sides by the LCD. Now the LCD here is just a little bit tricky today because it involves, if I can draw a brace correctly, it involves the use of something called the difference of squares. All right, so difference of squares basically says if I have a squared minus b squared, that's going to be equal to a plus b times a minus b. And if you look at the actual problem that we're faced with, we have x squared minus 1. And these can be expressed as x squared minus 1 squared, which would look just like a squared minus b squared. Now, based on the identity here of the difference of squares, this should equal x plus 1 times x minus 1. So if you were tempted to take the LCD, or by just multiplying all the denominators together, you can kind of see here that we can just use this as the LCD, and it will take care of the denominators on the left-hand side, and will also take care of the denominator on the right-hand side. Since if we multiplied this back out, we would go right back to where we started. All right. So the LCD in this case that we're going to use is going to be x plus 1 times x minus 1. And we're going to multiply both sides by that. So I have x plus 1 times x minus 1 multiplied by negative 4x over x minus 1 plus x plus 1 times x minus 1 multiplied by 4 over x plus 1. And this is going to be equal to x plus 1 times x minus 1 multiplied by negative 8 over x squared minus 1. All right. Now, at this point, we're looking to cancel between the numerator and denominator of each term. So we see an x plus 1 cancel with the x minus 1 cancel with the x minus 1 in the denominator of the first term. We see that an x plus 1 cancels with an x plus 1 in the denominator of the second term. And then both x plus 1 and x minus 1 cancel out x squared minus 1 on the right-hand side. So just kind of updating what we have remaining. And I'm going to leave it in the same order, hoping that it will be less confusing when... Oh, forgot my x, didn't I? Less confusing when you're kind of seeing from line to line, and then I'll rearrange it. All right, so then this is going to be plus x minus 1 times 4 is going to be equal to just negative 8 on that side. All right. Now, you can rearrange it if you want. I'll go ahead and rearrange it just so that it looks a little nicer on the eyes. All right, plus 4 times x minus 1. This is going to be equal to negative 8. But, you could just distribute, I guess, backwards, if you will, and you don't have to rearrange it like this. All right, so now this looks like something that we can solve. We will end up with some quadratic solutions here, so just keep that in mind. So we're going to have to just verify that they don't violate any of the denominators that we have in our original problem. All right, so now at this point, let's just go ahead and distribute the negative 4x through x and that 1. We're going to distribute the 4 through these two terms. So end up with negative 4x squared minus 4x plus 4x minus 4 equals negative 8. Let's double check we did that correctly. Negative 4x squared minus 4x plus 4x minus 4 equals negative 8. Awesome. Now we're ready to combine like terms. What I'm going to do, I'm going to combine like terms here and here. Those two are going to cancel. And I'm also going to add 4 to both sides. So I end up with negative 4x squared equals negative 8 plus 4 is negative 4. And now I need to get the x squared term by itself so that I can use the square root property. Dividing both sides by negative 4. Cancels on the left side, so I would end up with x squared. Negative 4 divided by negative 4 is positive 1. And now I can utilize the square root property here. All right, I'll take the square root of both sides. And on the right-hand side, we're going to remember to add a plus or minus here. The radical and the exponent cancel on the left. X equals plus or minus. And the square root of 1 is just going to be 1. So your proposed solution set we're going to have x equals negative 1 and x equals positive 1. And let's see if either of those causes an issue in our original problem. So the proposed solutions were x equals 1 and x equals negative 1. If x is equal to 1, it would cause issues here as well as here. So x cannot be equal to positive 1. If x is equal to negative 1, it will cause issues here as well as here. So x equals negative 1 is not included as well. So what is the solution set then? Well, the solution set is going to be, you can do it like that. It's the empty set. You can write the empty set like this, or you can write no solution. Again, all of this can be found on our OneNote notebook. All right. Okay, let's talk about work rate problems. So with work rate problems, pretty much you're kind of analyzing the amount of time it takes someone or something to complete a job and the type of situations you'll find yourself in. You'll have these situations where maybe there are two people and both of these people are working together to complete a job. So maybe you and a friend are shoveling your driveway. Maybe you shovel faster because it's yours and you know how you want it. But both of you are working together. So we'll find expressions that represent your work rate, and we would add those two together because you all are working on the same project and contributing to the same effort. Okay. There are other situations where one of the two people or things are working against each other. For example, maybe you're raking the yard with your, leaves in the fall with your sibling, and you rake all the leaves up in a pile and they run and jump in the pile. So you have a certain work rate to where you're completing the job, and they have a certain work rate where they're actually like taking away from completing the job. So in that case, we would subtract those situations. We will find problems for both of the scenarios that I've listed, but I just want you to be on the lookout for that when you are working through my math lab. Are the two things working together, or three things, or however many things there are? Are they all working together, or are they working against one another? If a job can be done in t units of time, all right, so t, we're talking about units here, of time, that is, then the rate of work, R, is 1 over t. Now, this formula I would like to modify a little bit. I would like to just add a little r here so that when we talk about the rate of work or work rate for a person, that this is going to be 1 over the time required to complete a job. Because when you think about it, maybe it takes you 2 hours to clean up your room, but you only work for an hour, right? So we have a time required parameter for time, but we also have a time actual, which is the amount of time we spend working, all right? So going on down here to this paragraph, it says, the amount of work completed, A, is found by multiplying the rate of work, R, and the amount of time worked, T. You see how they're using T again? So they say that this formula, A, which stands for the amount of work, is equal to R multiplied by the time spent working. So we're going to call that time actual. So this is time actual. This is time we actually spend working. For example, if it takes us an hour to bake a dozen cookies, right, and we bake for 4 hours, we should have 4 dozen cookies, right? So I would like to add this modification to the formulas to help you understand, okay, which of them am I plugging in for? Which one of them am I getting? Because just writing T doesn't really tell you, whether or not it's the time required or the time you actually spend working. Okay, so with those two formulas, we can solve any of these work rate problems. One printer can do the job twice as fast as another. Working together, both printers can do the job in 2 hours. How long would it take each printer, working alone, to do the job? Okay, so the job is a clue. Both printers can do the job in 2 hours is a clue. And also one printer can do a job twice as fast as another. So when we come down to our formulas, we have R equals 1 over T sub R, which is the time required. And we got, we'll go fast, slow. All right. So then we have actual, or your amount of the job completed. That's going to be R times T sub A. All right, so we're going to use both of these. First things first, let's define some work rates real quick. We don't know what the work rates are, so we're going to have to use X here. Now, if a one printer can do the job twice as fast as another, that means the time, and let me scoot this on down, yeehaw this with the lasso tool. All right. So now we can start to think about, okay, T sub R here, time required. All right. Now, if it takes the fast printer, this works twice as fast now. If it takes the fast printer X amount of hours to do the job, because it works twice as fast as the slow printer, then it should take the slow printer 2X. Like if I do the job twice as fast as you might do the job in 4 hours. I'm going to do the job in 2 hours. All right. So you can either define it like this, or another way you can represent it, and I think this is how the book does it. It says one printer can do the job twice as fast as another. All right. So if we're thinking, okay, so we're using the slow printer to define the fast one, right? So it's going to take the slow printer X amount of time, and it's going to take the fast printer half that amount of time to complete the job. So you can either do it like we said before, where I make the fast printer X and I make the slow printer 2X, or I can say I can set X as the slow printer and just take half of the fast printer. This really is going to depend on how you interpret the problem. Either way, either one of these will work. I just want to provide a diverse amount of ways that someone could think about this type of problem. All right. So now going on to our 1 over T sub r, I'm going to use, because this is how I think about it. I think about it in this way. Hey, maybe use it this way. But they both will give you the same answer. So I think about it in this kind of manner here. So when I write out my formulas here, this is going to be R sub F, which means this is the work rate of the fast printer. That's going to be equal to 1 over X. Then I have R sub S. This represents the work rate of the slow printer. This is going to be 1 over 2X. All right. Now, moving right along, we can go ahead and make an equation that represents what we have going on using the amount of time worked formula here. So the amount of time worked formula, this one's going to end up being A, the amount of work completed, is equal to R. Now R is going to be comprised of both of these two. Since they are working together, we're going to add the work rates of the fast and slow printers. They also told us how much time they would be working. All right, but maybe what I should do, let me just back up real quick. Just back up, because I want to give you something a little more general, and then we'll substitute these things in. So this is going to be R sub F plus R sub S. And we're going to multiply this by the time actually spent working. All right, and I'm going to solve this over on the side here, but I just wanted to give you a little more of an idea, a little better idea of how to arrange a situation when you have two counterparts working towards the same goal. All right, so the amount of a job completed, there's going to be one job completed, and that's where the job comes into play. That's our context clue there. So it's going to be one job completed. That's going to be equal to the work rate of the fast printer plus the work rate of the slow printer. Now, how many hours do they actually spend working? They spend 2 hours working. Now, let's solve this. I would multiply the 2 through both of these terms. So I have 1 is equal to 2 over x plus 2 over 2x. Now, in the second term, the 2's cancel. So I'd be left with 1 equals 2 over x plus 1 over x. Do they have the same denominators? Yeah, they do. So since they have the same denominators, we can add the numerators. 2 plus 1 is 3. Now, this is when people want to cross multiply. Please don't make me want to reevaluate my career choices. Instead, we're going to multiply both sides by x. And what we end up with is x equals 3. Now we have to ask ourselves, hey, what does x mean? What does this represent? All right. X equals 3 represents the time it takes, in my case, the fast printer to complete the job. All right. So x equals 3 is the time it takes for the fast printer to keep the job or to complete the job. Fast printers required time. Now, since the fast printer works twice as fast as a slow printer, this means that the slow printer required time is going to be 6 hours. hope this helps. Okay, so next I want to introduce the power property to you all. Pretty much this allows us to raise both sides of an equation to an exponent. That's basically what the power property is allowing us to do here. So that's why it says P equals Q. Then the solutions of P equals Q are also solutions of P to the power of N equals Q to the power of N. Now, this is great because we maintain the solution set utilizing the power property. All right, so when we're dealing with radicals, we want to go through these steps. I'll allow you to read those steps. And let's walk through the problem. So the first step wanted us to isolate the radical. Then we needed to take the square root, we needed to square both sides so we can eliminate the square root on the right-hand side. So we square both sides. That eliminates what we have here. We end up with x squared equals 15 minus 2x here. Now you need to put this in standard form. So you can go ahead and add 2x to both sides. You can subtract 15. And then you can solve this quadratic equation. Now it looks like this one. Yep, this one can be factored. So you may factor it. You may complete this. You don't need to complete the square. You may factor it, or you may use the quadratic formula there. You can complete the square as well. Now, let's take a look at what's going on with the solution set. So we get proposed solutions of x equals -5 or x equals 3. Now, what you want to do is plug these into the original. Just kind of touching on a piece that we'll need later with domains. But when it comes to square roots, you can go ahead and set the inside equal to 0 and solve. And it'll let you know what the boundary point is. So 2x equals 15. So x equals 15 over 2 is a boundary point for us there. All right. So what I mean is, as we, and this is going to be like 7, what is that? This will be 7.5. So if I plug in, wait, hold up real quickly. Let me look. I'll plug in -5. Plug in -5 here. I'll end up, oh, actually, I see what's going on. So we need to get a true statement. That's what's wrong here. So I'm actually going off on a tangent here. We'll talk about the square root here another time. But what the problem is when we plug in -5 for this problem, what ends up happening is we have -5 minus the square root of, this is going to be boom, boom. We end up with 2 times 5, which is 10. So we have 25 here. Now this is -5 minus 5 equals 0. And that's not true because we end up with -10 equals 0, and that's not a true statement. That's why we exclude -5. Right. It's not a domain issue. At first I thought it was a domain issue, but that's not what they're getting at here. So we actually need to plug both of these in to confirm that we get a true statement. That's the purpose of this particular challenge. All right, so let's see what we get with this one. That's 3 minus, now 2 times 3 is 6. 15 minus 6 is 9. Is 3 minus 3 equal to 0? Yes, that's a true statement. So that's why our solution set is going to be 3. All right, so we have examples. Let's see how many examples we have. We have 5. Do we have 6? I'm sure we have 6 too. 6, 7. And we have some U substitution with 8. I think 8 is the last one. No, we have 9 too. They're all U substitution. We'll talk about U substitution in a separate video. But I wanted to get you started with work rate as well as the first part of this, lecture. So I will come back and make a video about example 5 through 9, and we will go through. Actually, you know what? I'm gonna make a separate video on U substitution. So you should see 3 videos from this lecture today, and hope you enjoyed the first. Peace.